As I've mentioned before, alkynes are one of our best carbon-carbon bond-forming tools in Organic 1. And I've taught you how to take an alkyne and convert it into useful things. But none of this is very useful if you can't make an alkyne in the first place. And now that we've done E2 elimination, you're really set up to understand how we make alkynes. So here we have dibromo substituents, which are the key to making an alkyne, because what you need to do is run a pair of E2 reactions. And the first one's easy, but the second one's always harder, which is why you need relatively forcing conditions, either a really strong base or potentially a lot of a milder base, and possibly some abuse in the form of heat. When you're drawing out a mechanism, of course, it's always valuable to go ahead and draw out the compound over the arrow in Lewis structure form. And LDA, of course, is lithium diisopropyl amide, which is a very strong base with pKa of about 42. And even if you don't remember that, remembering that the pKa of the N- is going to be 35 or thereabouts. So this is a very strong base. Lurking in our starting material, this would be a vicinal dibromo. In other words, the bromines on carbons that are adjacent to each other, not the same one. Then we can go ahead and do a E2 elimination. And since this is a large and bulky base, it's going to abstract the easier to get to hydrogens first. And it's simply going to pull them off, and that will lead to the expected double bond product after kicking out the bromine. So the intermediate compound that's formed first is going to be this one as drawn. And then, of course, we have two equivalents of LDA, which means we have two of these molecules for every one of those. So a second one can come along and now do the second sequential E2 elimination product, which then leads to the expected alkyne as follows. And in fact, you could at this point, because the pKa of this hydrogen now is going to be on the order of 25, in fact, drive this reaction to completion by using, say, 3 equivalents of LDA, which would then convert this into the deprotonated product. This part's not necessary, but it would be one way of guaranteeing that this material is processed fully into products. It drives it to completion. It does not matter if you work with the vicinal dibromo species or the geminal dibromo species, you're going to have similar things taking place. In this case, the sodium hydroxide is not nearly as strong of a base. Its pKa is only about 16, but you are using a lot of it, and you are also heating it up. So both of those will tend to drive things along as well. This will deprotonate, cause a double bond to form, kick out a bromine. The first intermediate product that we form here is going to be analogous to the double bond material shown up there. Again, we have excess hydroxide, so a second one can come in and do the deprotonation and kick this out. And again, the product is going to be identical. And again, in this case, since the pKa of this particular proton is about 25 and the hydroxide is only about 16, you cannot drive things onto completion because it is not strong enough to do the deprotonation. So with LDA, a much stronger base, you could add 3 equivalents and deprotonate. With hydroxide, you're really going to go here and stop. You would need to isolate this material and then deprotonate it with a stronger base in order to use it in further synthesis. And as mentioned in the previous video, several of the techniques that you could use here would be to deprotonate with sodium hydride, which has a pKa of about 35. You could deprotonate with sodium amide, which likewise has a pKa of about 35. Or you could deprotonate with LDA, which as mentioned here, has a pKa of about 42. So those would be the plausible bases that you would use to convert this into the deprotonated material, which is ready then for SN2 type reactions, as long as you're reacting with primary substrates.